Everyone, my name is Chad Collett from SubC Imaging. I'm CEO and founder. I'm here to present imaging solutions for marine science, and what we're doing is an evidence-based approach to applications for underwater solutions.
Well, thank you, Chad. So good afternoon, and everyone. Welcome to the Scripps Technical Forum. I want to extend a welcome to those joining us for the first time, and for those who are regular attendees, it's always nice to have you join in. I'm Douglas Alden. I'm a research and development engineer with the Center for Western Weather and Water Extremes here at Scripps. In addition, I function as the STF chair and get assistance setting up and running the STF for my colleagues, Gwen Nero and Vanessa Scott. Gwen is Director of Corporate Affiliates, Business Development, Industry Outreach and Innovation, and Vanessa is an Industry Relations and Innovations Analyst. And I just want to point out that if you missed any of our recent Scripps Technical Forum presentations, they have been recorded and are available on the Scripps Oceanography YouTube channel. And there's a specific playlist for the Technical Forum. I wholeheartedly suggest you guys check it out. And please know that today's presentation is being recorded so that it can go up on the YouTube channel. And you've all been muted, but if you have any questions, you can use the Q&A function or just unmute yourself at any point. And with that, we're going to move over to the presentation from Chad. Thank you.
Thanks, Douglas. So as I mentioned, an evidence-based approach. I'm going to share my screen first, actually. Here we go. So the format of this webinar is, first we'll just go over who SubC is, in case you haven't heard of us, and then a few solutions and capabilities that we are demonstrating or showing, and then a quick product demonstration of a product and a service, actually, and then some scientific studies. So the evidence of that our equipment's been used in the field for years now by marine researchers worldwide. So SubC's mission is to continuously create the most technically advanced and intelligent video systems. And just 1 second now. There we go. Okay, sorry about that. So here's what our customers are saying about us. There's a few quotes here. I'm going to give you some time to read it in case you need it. We do have time for this meeting. But essentially, what Dr. Frederick Abig is saying here is that some of the image quality is very good, and some of the features there, such as downloading stills in real time, make things easier. And that's one of our goals, is to make things easier for researchers. What Ron Bernier is saying down below there is that we give good tech support. So our team is here to help, and we're very patient, and we are always here to remote into a system to do any troubleshooting to get you to back on track as fast as possible. We have customers all over the world, from the Netherlands to Germany and the United States and China and everywhere in between. We've got over 130 clients worldwide, and we've been in business for 10 years. You can see a few different universities and institutions we work with. This is a short list. We have high-resolution digital stills in sync with underwater LED strobes. You can see in the image here, this is showing an ROV, but these solutions and capabilities are compatible with all underwater systems. We can also record 4K and HD, 2 cameras internally, and to 512 gigabytes of storage. We have something on the back of the cameras called aux ports. With these aux ports, it allows plug and play control of LEDs as strobe or as a lamp, as well as lasers. So that could be line laser, which you can see in the image there, or parallel dot lasers or grid lasers. one thing to note on the aux ports actually is they also control pan and tilts, and you can have NMEA formatted sensors connected to do data logging, which there's a slide about up ahead. We also have a SubC video recorder. So the DVRO, as it's called, can record 6 channels of video with black box and overlay. The overlay is shown, it can be shown as graphics or as text. And with the dynamic video overlay, you can add some graphics to contain different types of overlay and different types of data. This solution is compatible with all video formats, including IP cameras, SDI, and composite, and all legacy formats as well. We also have an autonomous solution that can run on batteries or on an AUV, which will also have batteries. And this is used for time-lapse of video and digital stills. It has a built-in scripting that runs inside the camera. And with the scripting, which I'll show in the product demo, you can do some advanced capabilities, such as conditional statements. So say if your sensors are reading a certain value, it's possible to react to that and start recording. The camera is also a data logger. Our cameras are also data loggers, so you can record your depth, your altitude, and other values. Cameras also have a system time built in, so the camera can act as the center of the system. You can see here we're deploying a new towed frame system we're developing behind small watercraft, in this case a jet ski or Sea-Doo. And our goal with this system that's in development is to make it deployable from as small a craft as possible. Sea-Doo, I think, is 8 or 10 feet long, so that then deployment from a larger vessel will be much easier. With this system and with our cameras, you can record 4K video continuously, and you can also record digital stills at 21 megapixels up to 4 hertz for image mosaics and other applications. Also with this system, you get real-time HD video and control over up to 400 meters of cable. So that enables some lower cost applications, such as towed video of coral reefs or other areas, or geology studies in shallow water, and shallow water being less than 500 meters. Since 2013, we've been working with University of Washington and other observatories delivering solutions for marine studies. So we provided Ethernet digital cameras, lighting, and related services to support the objectives of the National Science Foundation's Ocean Observatories Initiative. So this is a picture of their observatory watching a hydrothermal vent, and you can see, you can actually see a live feed of this in real time from their observatory, I guess you would call it interface, but it's online. And these cameras and equipment are all full titanium. And since this project, we've standardized on titanium as our standard build. The cameras in these cases can control the LEDs and lasers and pan and tilt and other sensors directly through the aux ports. And all of our cameras now have integrated Ivanhoe designs as an option. And with this Ivanhoe based design, you can get one-to-one water corrected video and images without very much distortion, and much higher sharpness than if you just had a flat acrylic or BK7 port. They also are low distortion as well. Here's a video I'm going to bring up. This may not play through incredibly crisp, I guess, through Zoom, but it will. There are links on our YouTube videos, or links on our YouTube channel to the videos if you want to view them later. So in this image, in this video, you can see it's a comparison between flat port and our liquid optics and our ultra optics, which are our different options. So with the flat port view, you can see not quite crisp, but then with liquid optics, you can see it's much crisper. And when it switches to ultra optics, you can see the same field of view, or the camera's in the same placement, but the field of view is much wider, so you get a wider perspective. And that's a side by side. One second. Okay. So this is our real-time remote streaming service. And with this service, it's a new service that we're developing. It runs in the cloud and has a secure login interface. It's meant for energy and science users who need to see real-time video from SubC to their office. It's really easy to get started with this service. If you need more information, feel free to contact us and we can set you up with a free 30-day trial. So this, we'll start the product demonstration part of the webinar now. First product I'm going to show you is the real-time streaming service. Actually, I'll show you the output from it. We have an observatory we've set up here in Newfoundland. This is something my kids were watching. In a second, sorry. So this is the observatory running here in Clareville. And I'm going to send you a link to this in the Zoom chat. Bring that up. How do I bring that up? I'll send it out after this meeting, actually. And you'll be able to, this will still be running. You'll be able to bring it up anytime.
Can I jump in with a question? This is Douglas.
Go ahead, Douglas.
Yeah, so I was just curious, what do you do to keep the lenses from fouling? I mean, how long do you expect to be able to deploy them without that becoming a degradation issue with the cameras?
So that actually depends on what depth you're operating in. If you're in, say, shallow water or less than, say, 300 meters, which is about as deep as light penetrates, then you won't, you'll get marine growth that has to be cleared in some way. There's a lot of studies that have been done around UV lights, and that's one effective way of clearing it. And some other researchers have used marine grade wipers that go on the front of the cameras. There's a few different options there. Deeper water, like University of Washington and University of Victoria with their Neptune and OOI observatories, they just actually, at the end of a cycle of collecting video or images, they'll tilt the pan tilt down with the camera on it. And because the only type of growth you'll get is a marine snow. It won't actually be a growth. It's just marine snow that's falling. And if you have the camera pointed up, you'll collect growth on the front. So
when you're operating in the photic zone, is that an option for these cameras that you provide the wipers, or is that something that is custom built by the end user?
That's a great question, Douglas. So that's one thing where SubC differentiates itself. We will work with researchers to integrate custom components like that, either on an NRE basis or as a standard feature if it's something we view we can offer other clients.
Great, thank you.
Thank you. I can't quite figure out how to send out the chat. Douglas, do you know?
There should be down on the bottom of the screen, there's a little icon for chat in the Zoom window.
Oh, I found it. Okay.
Yep.
Okay, here's the link to view a real-time feed of this stream. The stream is being transmitted on a low bandwidth connection, and that's one of the unique points about this this service. It can work over satellite links that have even as low as 64 kilobits a second of bandwidth. And it's a secure feed. We've disabled the secure feed right now of this stream, but it's usually a login with a username and password to get to the feed. So in the future, we'll be enabling YouTube type streaming for this on request, but right now this is more of a private feed for offshore researchers and offshore energy applications. Back to the presentation now. I'll bring up the Rayfin camera. So this, you can see it. I believe I'm still presenting my screen. So this is our Rayfin camera system. This camera is running in our tank, and it's a 10-meter tank. So just to give you the kind of scale here. And on the top here, you can see the depth. So there's a depth sensor built into this specific camera. It's a 600 bar sensor. So that's a 6,000 meter sensor. So it's only in, a little bit of water here, which is why it's fluctuating. And the resolution is spread over that 6,000 meters. It's also got a heading, tilt, and roll sensor building, or IMU, or orientation sensor. And that data is all fed up in real time to the interface. There's strobe compensation controls. You can turn on and off your strobe. And there's also exposure control. So we can adjust our shutter speed dynamically, and we can put everything in full auto as well. And the camera will adjust it in real time. And we can adjust the exposure value. So that's the bias applied to the auto exposure. So I'll put in manual, and there's manual and autofocus controls as well. On the left here, we can see recording settings. So you can set the file name as well as the file structure and directory it's stored to. You can add tags to the file names as well. So if I want to add milliseconds, I can do so. You can get very precise with the timing of the images and when they're taken. And you can set the record quality from SD to 4K, and that will change dynamically how much storage is remaining on the solid state drive inside the camera. Half of the storage, or more than half the storage, is taken up with this camera now. And it can be downloaded in real time and cleared by the operator. So there should be a lot of videos in here and digital stills.
Is that camera, is that the one using the 512 megabyte, or is that using the 12 terabyte?
This is the 512, yes. So it's 12 terabytes that can go in our topside video recorder, and that is a system where you've got multiple solid state or platter drives that you can insert. This camera has a 512 gig limit right now. We're actually currently testing a 1 terabyte card on request. Again, similar to integrating other sensors and other capabilities, we can do those things on request. So if you need more storage, that's something we can look into. Similar to the photo naming conventions, the same can be done with, or the video naming conventions, we do the same with digital stills, tags, image formats from JPEG and RAW, and we can also do continuous photos up to 4 Hertz. So the way you enable continuous photos is to hold down the stills button, and it'll keep taking digital stills until it fills up the hard drive. You can stop that by clicking. White balance controls, because sometimes you're operating in shallow water. So if I put it in auto, a little bit of green there, I put it in shallow water mode, should remove a little bit of that green and kind of return the natural color that we're looking for there. If we want, we can, maybe there's a little too much red here, you can adjust that as well based on preference. You can lock in your white balance. This is good for applications such as photogrammetry, 3D modeling, where you don't want a lot of change between your images of the white balance. So you would want a manual white balance, so the system's not changing that. Similar with the exposure controls, with those types of operations, you usually want the same settings between images so that you have a common RGB color per pixel. So I already went into this once, but this is the live view of the images and video as they're taken. So you can view images in real time while sending back video in real time. That concurrent operation means that one researcher or operator can be using the camera and doing the survey, while another is reviewing the photos and video to ensure that it is the quality that they require in real time. So you can have parallel operation. You can also store to a network attached storage device. That can be a network drive on board the vessel, somewhere else entirely. The camera's running on an ROV or a drop tow system, storing topside to the NAS. And because we have an LED plugged into the aux port, we're getting LED controls. So we can change the amount of light, and we can also turn on and off the laser that's connected. The aux device control panel is right here, and you can change the devices in real time. So as I remove the laser control disappears. So we've got our manta ray lasers connected, and when they connect, they turn on. Here it shows static or DHCP connection. Here's some video input controls. This is the stream quality. So right now we're streaming at 1080 at 10 megabits per second. We can change that to low bit rate depending on the system Ethernet bandwidth. So system being your underwater system, and it's Ethernet connection to the ship or boat. A streaming interface, so you can also stream over the internet using our service. This is the time control for the camera, so you can set an online time code or NTP server. You can also sync up with a local NTP server on board the vessel or in the system as well. So say in the case of an AUV, the AUV may have an NTP server that all of the sensors are using for calibration for everything to be zeroed for a common timestamp. You can also manually set the time, and the camera will maintain its own system time. This is an interesting feature. So the camera is also a full it's a full operating system as well. So it can run autonomously scripts that you write, and you can write the scripts within the camera interface here. So what this script will do is it will set the exposure, it will set the formatting wherever we want here with strobe enabled. It'll set the file names, and what I'm going to do is I'm going to run this script now, and you'll see it in action. So as it goes, it'll flick back to auto exposure, set the format to JPEG, enable the strobe, set the file names, set the video resolution and the bit rate, set the video name, the max duration, the clip size. It'll turn on the light. This is just so if you're running on batteries, what it's doing now is just going through a couple different functions so that you know it's operating. Imagine if you can't see video, but you can see the light flashing, you know that it's starting the script and the camera is powered up. So what these two, I'll do a little bit of a deeper dive into this, but what these two functions are doing is, this is a concurrent. So what that means is it'll run these two functions at the same time, and it will repeat recording and then wait for 20,000 milliseconds, which is 20 seconds. And then it'll stop recording, wait for another 20 seconds, and it'll keep doing that forever, -1. And it will also take pictures every 5 seconds. So what it's doing now is it's taking pictures every 20 seconds, or taking recording clips for 20 seconds, and then stopping for 20 seconds, and in between, at the same time, taking pictures every 5 seconds. So this camera can take pictures while recording video. While recording 1080p video.
Hey, Chad, we had a question from one of the attendees. It's for an integrated unit, i.e. an AUV, do you offer an API? And similarly, have you or have any of your customers built any Python or C++ libraries for operation and logging from a single board computer?
Awesome question. So the camera uses a full open API that we've developed, and it's available online. You can see the full API running here in the background. There's a lot going on, obviously, but what we're sending back is a lot of data that you can use. So if I stop, I think I need to stop script. There we go. Stop script. So we shouldn't be running anymore. Not this. There we go. Okay. So any command that you send that you can see here, and anything you send down here from the API will operate. So what you can do is use this advanced panel here to test API commands, and then you can take those commands and write a script. So I can make a new script. And if I see an API command, start recording. And if you see a function like that, you do any of the commands that are used from the software. So if I turn off strobe, you should see that here. Strobe disable strobe, and it says is strobe disabled false, right? And if I change the exposure, see all the focus exposures here, or all the focus commands. And yeah, you can use all of those functions in your scripting. So it should start recording, and that's it. So if you want to do something simple, like when the camera starts up, starts recording, you can do that very simply with execute on start recording. Of course, you'd probably want to add a bunch of other parameters like bit rates and things that you can control there. But yes, you can do all of that. And we're here to help as well. So we have customers in universities and institutions who are integrating these cameras and writing their own Python scripts to download footage over this integrated Samba server in real time. We're using Samba, which is another standard format for our file system access. So that's all open as well. And you can go in and take these photos off in real time on a Python script or on a different kind of script. I think that might answer your question. Okay, so at this time, if there's no other questions for this portion, I'm going to go back to the presentation and show you some example scientific studies. Zoom has overlapped everything here. 1 second. All right, so this study, which I'll play. There we go. So this study was led by Professor Craig Smith of University of Hawaii and Professor Lisa Levin from Scripps and Dr. Fabio De Leo from Ocean Networks Canada and University of Victoria. They've been using our observatory solution, or one of our observatory solutions, for their underwater study in Barkley Canyon since 2014. In May of 2014, 3 humpback whale ribs sections and 1 block of Douglas fir and a block of authentic orthogenetic carbonate were placed at a depth of 590 meters inside Barkley Canyon at a site in Ocean Networks Canada's Neptune Observatory. The purpose of this experiment is to monitor changes triggered by the implantation of various organic and inorganic substrates, as well as monitor how benthic organisms utilize the sparse food resources available in deep sea settings. So on a schedule of every 2 hours, the autonomous subsea cameras and LEDs pan to the 3 substrates while holding its position for 1 minute each. It captured 5-minute videos, and this was over years. So there's been a couple papers published from this, and they're still doing more studies over time. It's still an ongoing study since 2014. So it's a very long-term application, time-lapse application used using our equipment and using this very cool and interesting observatory station they've set up. One second, I'll bring up this video. So constantly testing and refining products is how SubC continues to remain at the forefront of SubC imaging technology today. It also allows us the opportunity to explore our home. So during the summer here in Newfoundland, we have something called a food fishery for Atlantic cod, which we call fish. If you're eating fish, it's usually cod here. While testing the SubC Rayfin Smart Camera with my grandfather, actually, myself and him were out in his aluminum boat. You should see there in a couple clips, or you may have already seen the cod jigger or fishing hook here. There's a lot of cod in the area. They're actually not biting at this time of year because you can see the cod jigger on the right there. They're not biting this time of year because they're actually full of capelin, which is another staple bait fish, which attracts a lot of different species of shark and whales and seabirds. It's one of the core, I guess, fish of the North Atlantic, and especially in Newfoundland. So these cod are all what we would say glutted or full of capelin. So we routinely do testing like this in the ocean here in North Atlantic because it is a harsh environment, and it's just interesting, and we very much enjoy it, of course. So Woodsole Oceanographic, WHOI, set out to sea for 3 weeks on the RV Atlantis from Gulfport, Massachusetts, equipped with a newly designed Alvin submersible and the autonomous underwater vehicle Sentry, and visited some of the most spectacular Lophili reefs known, and explored the deep sea for new reef habitats. Corals were collected and kept alive in order to determine if some of them are more resistant to ocean acidification than others. This may help preserve Lophili reefs in the future by identifying some resistant strains of deep sea coral to ocean acidification. So this video was used in the Acid Horizons documentary, which has won awards at some film festivals. And a link to the site for the documentary is in the presentation slide, at acidhorizons.com. I encourage you to go check it out. It's really cool, really interesting, and great science that they conducted. So most subsea projects require many components. Integration of these components can lead to high costs and complexity. To help reduce these high cost complexity, our systems are like Swiss Army knives. They're able to deliver multiple features in one package, meaning that you won't require multiple instruments, as everything you need is fully integrated into a single system. We are trusted by customers around the world. Our subsea camera systems are well known for industry-leading optics. Quality inspections and research rely on capturing the best images possible, and our cameras go above and beyond, especially in deep water and low light environments. These systems are easily adapted to meet your requirements. We have systems for everything from ROVs, autonomous systems, drop camera systems, observatories, and we're constantly adding new capabilities and new features based on customer requests. And that is the end of our webinar or presentation here. Do you have any questions?
There's nothing up on the chat or the Q&A at this time, but please feel free to reach out if you do, anybody that's attending have any questions.
I've got something to add here, actually. So I forgot to mention, so a couple years ago, we've been working with a team called Project Colossal out of San Diego for a number of years now. And a couple years ago, SubC partnered with Global Ocean Design, a guy named Kevin Hardy, who used to work at Scripps actually, and another person, Matt Mulrennan, who's head of Project Colossal. It's a not-for-profit. So our goal was to develop a low-cost deployment system to enable benthic ecology from ships of opportunity. So we won a Conservation X Prize, actually, in 2018 for that system. And the goal of the Connex prizes to build an ecosystem of early stage conservation technology products and solutions. So what we did was enable a lower cost solution for achieving some science. You don't necessarily need a large research vessel. You can go on a vessel, 20 feet and below, 20 feet in length and below, and collect some really compelling footage.
I had a question. I was just wondering what is the imaging sensor you use in the camera?
Our imaging sensors are primarily built from Sony. SubC actually designs and manufactures our own electronics. We develop our own subsystems. We've actually rewritten a version of Android, and we have an app that runs in our camera that is the OS. And our topside control systems are built in Windows using that API. So it's a Windows to Android kind of interface. So it's a full, and our mechanical designs are obviously designed by us as well. Most things are procured from the US and Canada, a couple parts from Germany, and sensors from Japan, of course, and all assembled here in Canada.
And then you mentioned in there that you can run this off of a battery pack. Is that something that you offer as an option, or is that something that just the customer would provide?
Absolutely, we can offer a battery pack, the camera, and the lighting, and the lasers, and whatever other components you require, and we'll actually test all of it together, ensure it works, and deliver a fully working solution for you.
Yeah, so we got a question. Can you elaborate on the power considerations for the battery operated units?
Absolutely. So we'll get your requirements for duration and what type of cycles you want to run. So if you want to take pictures every 10 minutes for 2 weeks, we can source the power required for that, or the batteries required for that. And we have spreadsheets to calculate the amount of power draw. We have all of that data on all of our equipment, of course, and any other equipment that you would want to run. You can provide the power draw data, and we can work that into our equations and give you a deployment time in days and fractions of a day.
And are those battery packs rechargeable, or are they primary cell?
They're rechargeable. We don't like selling things that are single use.
Great.
And if we don't have it, we'll let you know where to get it. Essentially, we don't need to supply everything. We would prefer to supply the things that we understand. If you source something, if you would like us to integrate it, it'd be better to send it to us, and we can make sure that everything works together. Okay.
Well, it doesn't look like we have any further questions. So with that, I'd like to thank Chad and SubC Imaging for their presentation today. I'm going to do a quick screen share here. I got a requested remote control from you, Chad.
Approved.
Okay. So, did my screen pop up? It didn't pop up. Share screen, hang on. Get it, there we go. All right, so I just wanted to thank Chad for the talk today. I think it's a really unique technology and kind of cutting edge in that space. And just say that coming up in the later this month, we have Regal laser measurement systems. We'll be making a presentation on LiDAR and its applications. I don't know specifically what their subject matter is, but I know that LiDAR has been used by the Airborne Snow Observatory here in California to look at the snowpack and our water supply, as well as we've got a group here at MPL that uses LiDAR to measure waves. In September, Geospectrum Technologies Incorporated will be focused a talk on underwater acoustics. And then in October, we have Turner Designs makes submersible fluorometers and sensors. And as always, we welcome input on future speakers. So if you've attended the STF in the past, I always put a call out there for topics or for either on campus or people that you know in the industries that you feel would be helpful to our research here at the university. So please reach out to me if you can. And with that, I'd like to thank Chad, and that's the end of our presentation today. Thank you.
Thanks, Douglas. Thanks, Vanessa, and everyone at Scripps.
Have a good day.
You too.